Hello, today we're going to talk about real zeros of polynomial functions. So the real zeros of polynomial functions correspond to the x-intercepts of the graph of the polynomial. While working with quadratic functions, polynomials of degree 2, we considered factoring to solve. So we're going to kind of generalize and expand on that approach as we look into higher degree polynomials. So a corollary of the remainder theorem is the factor theorem. A polynomial f of x has a factor x minus k if and only if f of k equals 0. So if it's a 0, if k gives us a 0, then x minus k is a factor. So we can look at this graph. I use the graph and the factor theorem to list the factors of f of x. Assume that all zeros are integers. So if we take a look up here, let's see what our zeros are. We have a 0 here at -1. We have a 0 here at +1. And 2, 3. It looks like we have a 0 here at x equals 3. So if we have a 0 at x equals -1, then we have, I'm going to write it over here as a 0. Over here we have a factor x plus 1, a factor of x minus 1, a factor of x minus 3. We're just moving the number to the other side to make it a factor. And so we can rewrite this as a polynomial f of x in factored form, x plus 1 times x minus 1 times x minus 3. The relationship between zeros and factors cannot be stated enough. That's all we're doing. When we're factoring it, it's the same as finding zeros. Many times we have a factor in a polynomial that repeats, and we have a special term for that. We call that multiplicity. And the multiplicity is just a way of saying repeated factors. For a function f of x, the multiplicity of 0k is the number of times that x minus k is a factor of f of x. So if I have f of x equals x plus 2 cubed times x minus 1 squared times x minus 5, we say that x equals -2 is a 0 of multiplicity 3, x equals 1 is a 0 of multiplicity 2, and x equals 5 is a 0 of multiplicity 1. In general, we don't say multiplicity 1. We only state a multiplicity if it is greater than 1. So it's always assumed to be 1 unless we say otherwise. So that's a pretty important concept here. And check it out. If you have a multiplicity that's even, it's going to touch the x-axis at the 0. If you have a multiplicity that's odd, the graph of the polynomial will pass through the 0. So that's a quick and easy way of telling if you have an even or an odd multiplicity just by looking at the graph. Okay, so given some zeros, we can write the factored form. Instead of looking at the graph, what we have instead is we found two zeros of this polynomial. Notice that it's 2x squared. X squared, degree 2, has two zeros. So we could rewrite this polynomial as x minus 11, I went with pi, mathematician's habit, x minus 11 over 2, and x minus 7. And that's the completely factored form. We might instead write this as the 2x minus 11 instead of x minus 11 halves, but this will work out, and we'll just use integer coefficients after we simplify it all and multiply it out. For f of x equals x cubed minus 2x squared minus 5x plus 6, I know my zeros, so I know that this factors as a 0 of -2 is a factor of x plus 2, a 0 of 1 is a factor of x minus 1, and a 0 of 3 is a factor of x minus 3. You could make this harder, but why? Let it be easy. Let it be as straightforward as zeros turn into factors. And remember, if we have a 0, we can add 2 to the other side. Literally, this term is equal to 0 after we factor it, the 0 factor property. And so zeros going back to factors as we put them in here. All right. Another one, kind of blazing pretty quickly through these, but I think we're going to do all right. Use the graph to factor f of x equals -2x cubed plus 2x. Assume that all zeros are integers. So it looks like we have a 0 at -1. We have a 0 at 0. And we have a 0 at +1. So if we turn these all into factors, x minus 0, that's a little weird. Frequently, we will write that as just x. How often do we actually write minus 0 with a 0? Very rarely. And you can check factor out an x, and then we'll have the factor out a -2x, actually, and then we'll have a difference of squares, and that's where we get the x equals -1 and -2. Now, this is the problem. I did not include that -2 that factors out. So if you want to factor it correctly, you have to pay attention to that leading coefficient, which makes me wonder if I did it correctly up here. All right, the half is going to take care of our 2 coefficient in front. What do we do up here? Yeah, so we don't know the leading coefficient here. So possibly there's an a sub n, but possibly there is not. All right, so don't forget to pay attention to that leading coefficient. Scroll back down here slowly. Okay, but what if we don't know the zeros? What if we don't have a graph? Maybe I don't have my calculator with me, or whatever it might be at the time. If I know that k equals 1 is a 0 of this polynomial, then I can use synthetic division. Remember to write all the coefficients in descending order, putting in zeros if necessary. If the x squared term wasn't there, I'd put in a 0 in place of it. And then synthetic division, I'm going to drop the 1, multiply to go up and over, add straight down. -8 times 1 is -8. Add straight down, I get 15. Multiply times 1, I'll get 15. Add straight down, I get 0. And we know that this is going to be 0 because it says k equals 1 is a 0, so my remainder is definitely going to be 0. Remember, this is an x cubed, so down here we're going to have 1x squared minus 8x plus 15. Well, this is just a quadratic, and a quadratic we can factor. Two things that multiply to make x squared. I want to multiply to be 15. It's a positive 15, so it's negative in both places, right? Multiply to be positive, so they have to be the same sign. They have to add to be negative, so they must both be negative. Multiply to be 15, add to be 8. That's a -5 and a -3. So I can rewrite this in factored form. I know k equals 1 is a 0. So I know x minus 1 is a factor. And I've just found my other factors. A lot of times we only need one of them to reduce to a quadratic, and we could revert to some of our old skills there. All right. The rational zeros test. This one's pretty cool. The fact that this works is really, really incredible to me. Let f of x be a polynomial, right? A sub n, x to the n, and so on, where a sub n is not 0. So our leading coefficient cannot be 0. And this is just a polynomial function f with integer coefficients, so positive and negative counting numbers along with 0. If p over q is a rational number written in lowest terms, and if p over q is a 0 of f, then p is a factor of the constant term a sub 0, all right, constant term, and q is a factor of the leading coefficient. So numerator is a factor of the constant, excuse me, and q is a factor of the leading coefficient. Let's use this. Let's use the rational zeros test to find any rational zeros of this polynomial. So I'm going to write all fractions of the form p over q, where p are factors of the constant term, 1, 2, 3, and 6. And q are factors of the leading coefficient, that's 1, which tells us all possible rational zeros are plus and minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Now, it might not seem like that's very helpful, but it's given us 8 things to try in order to find at least one 0. And if I find one 0, then I could use the quadratic formula to find the others. So let's try 1. I always try 1 first. I always try to let it be the easiest one possible. So 1x cubed, 0x squared, minus 7x and the constant term. Drop the 1, multiply to go up and over, add straight down, multiply to go up and over, add straight down, multiply to go up and over, add straight down, and when I get the 0 remainder, I know that I have found a 0. So x equals 1 is a 0. And that's from the remainder theorem. Right? The remainder theorem says if the remainder upon division is 0, then x minus k is a factor of the polynomial. I also know that x squared plus x minus 6 is a quotient, right, when I divide by x minus 1. So if I want to find all the rational zeros, now I need to factor this. Well, I could factor a quadratic pretty easily. I could keep going with my rational zeros test. I could then divide by -1, 2, -2, 3, and so on, and keep going. But instead, to get x squared, we'll get x times x. We want to multiply to get a -6, so one of them's positive, one of them's negative. We want to multiply to get 6. They have different signs, and the bigger one is bigger by 1. So we're going to make it a +3 and a -2. And this is our polynomial in factored form. And we can now list our zeros as -3, +2, and +1. We didn't have to use the rational zeros test to find all of them. We just used the rational zeros test to reduce it a little bit so that we could find the rest of them as well. Let's use some orange here. All right, so again, P over Q. P is factors of the constant term. All factors of 6. Anything that goes into 6 is 1, 2, 3, and 6. Factors of 2 are 1 and 2. So this will make all plus or minus 1 over 1, 2 over 1, 3 over 1, 6 over 1, 1 over 2. 2 over 2 is the same as 1. 3 over 2. 6 over 2 is the same as 3. So this plus or minus, this is horrible notation. This is my lazy notation. This is a much better notation up in problem 1, where you write the plus or minus in front of each one. On some homework systems, you have to write 1, comma, -1, comma, 2, comma, -2, and so on. So be careful and pay attention to your homework system. Again, we want to try to divide by the easiest thing possible. So I'm going to start with 1. I always start with 1. 2x to the 4th, 1x cubed, minus 8x squared, minus 1x, and 6. Drop the 2, multiply to go up and over, add straight down. Multiply to go up and over, add straight down. Multiply, add, multiply, and add. And yeah, I picked some nice ones. They gave us the x equals 1 as a 0. So if I'm looking for zeros, I'm going to write these over here. X equals 1 is definitely a 0. But now this was an x to the 4th. This will be an x cubed. I can't factor an x cubed on my own, but I know that I can now ignore this remainder. Now I'm going to use 2, 3, -5, -6 as my quotient, and I'm going to try to put 1 into this. Let's get rid of this x cubed here. Why am I trying 1 again? Maybe it's a repeated 0. I don't want to ignore the fact that it could be a repeated 0, so I'm going to try it. Drop the 2, multiply to go up and over, add straight down, multiply to go up and over, add straight down, multiply to go up and over. So not a factor. That one's not going to work because my remainder is not 0. So I'm going to try again. This time I'm going to try a -1 into 2, 3, -5, -6. Yeah, I'm kind of cramming it in here. My spacing wasn't planned very well. Drop the 2, multiply by the -1 to go up and over, add straight down, multiply to go up and over, add straight down, multiply to go up and over, add straight down. Oh, look at that. -1 is also a 0. This was an x cubed, so this is x squared. I can now factor 2x squared plus x minus 6. This will be 2x times x. I want to multiply to get a negative, so it's a plus and a minus. But we can't be all willy-nilly with that. We have to think about how we're going to do this. It's a negative 6, so it could be plus and minus. It could be minus and plus. A little bit of trial and error here, guess and check, see how it works out. Now, I know if I multiply 6 times 2, I'm going to get 12, which is way too big. So what I'm thinking is, I'm going to multiply 2 times 2. Let's get all this junk out of here and write the correct number here. 2 times 2 makes 4x, and a minus 3x makes a positive x. Negative 3 times positive 2 is a positive 6. So I can now find my other zeros. My other zeros will be negative 2, and add 3, divide by 2. We have 3 halves. If we want to write our polynomial in completely factored form, which I believe was one of the instructions, we have f of x equals 2x minus 3 times x plus 2 times x plus 1 times x minus 1. Completely factored form with our zeros listed as well. And this wasn't difficult work, right? But you have to know what you're doing and how to do it and why you're doing it in order to get there. So the actual skill is not difficult. It's the knowledge leading into it. Now, instead of just randomly guessing, I don't know, let's try 1, let's try negative 1, let's try 2, let's try negative 2. Can you imagine if I would have kept trying until I got to positive 3 halves, kept doing the synthetic division? I'd use sheets and sheets of paper. But Descartes' rule of signs helps us narrow down those choices. So let p of x define a polynomial function with real coefficients and a non-zero constant term. All right, so we can't have a constant of 0. Terms are listed in descending powers of x. So the number of positive real zeros either equals the number of variations in sign occurring in the coefficients of p of x, or is less than the number of variations by a positive even integer. Okay, wait a minute. So see how this is positive and then negative and then positive and positive. We start positive, we change once, we change twice, no change. So there will be either 2 or 0 positive real zeros. All right. Now let's also do the negative. So the number of negative real zeros either equals the number of variations in sign occurring in the coefficients of p of negative x, or is less than the number of variations by a positive even integer. P of negative x will be negative 2x cubed. Any odd powers will change signs. Even powers will not. So here I'm negative, 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 switch to positive. So there is 1 negative real zero. And we can verify that using a calculator. So we can turn it on. Let's graph 2x cubed. Make sure you come out of the exponent. Minus 4x squared plus 2x plus 7. When we take a look at the graph, we see 1 negative real zero and 0 positive real zeros. And we know this because a cubic graph, the ends go in the opposite directions, right? The end behavior. A leading coefficient of 2 means it's generally increasing. So we know this is not going to come and turn back down at any point. We know that this is all we're going to get from the cubic. There's 1 negative real zero, and that's it, which tells us there's going to be some complex zeros in this particular example. All right, let's try it again. So for p of x, positive, 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 negative, there's only one change. If I look at p of negative x, I'll have 5x to the 4th plus 3x squared minus 2x minus 9. I'm positive, positive, one change to negative, and then I stay negative. Notice we cannot subtract an even integer from these to determine if there's more. Right? We're not going to have negative 1 real zeros. So let's graph it and check. 5x to the 4th plus 3x squared plus 2x minus 9. This is a 4th degree polynomial, so it's an even polynomial, so we know both ends of the graph are going to finish together. Leading coefficient is positive, so we know they're both going to finish up. So we know this graph is not going to turn back around and come back up. There's one negative 0, there's one positive 0, the other two zeros will be complex. All right, so we can verify this. This will help us if we use Descartes' rule of signs and we've already found one negative real 0, then when we're doing the rational zeros test, I'm not going to try any more negatives. Right? I'm only going to try, once I find the one positive, I'm done. I'm only going to look for negatives. Once I find that one negative, I don't have to keep going. Using these two together helps us find zeros of polynomial functions really quite easily. Okay, now the intermediate value theorem is a fantastic theorem. Let's talk about it. Let x1, y1 and x2, y2 be 2 points where the y values are not the same, so they're not at the same height. And we're just going to put an order on the x values just because we can. X1 has to be less than x2. If the y values aren't equal, then the x values can't be equal. These are 2 points on a continuous function f. So it's a continuous function, no breaks, no jumps, no gaps, no holes. Then on the interval from x1 to x2, with x in between, f must assume every value between y1 and y2 at least once. All right, so use the intermediate value theorem to show that f of x equals x cubed minus x minus 1 has a 0 for some x on the interval from 1 to 2. Okay, let's take a look at this. If I look at f of 1, let's just evaluate and see what happens. I end up with 1 minus 1 minus 1, which is a negative 1. If I evaluate at 2, I'll have 2 to the 3rd minus 2 minus 1, which is 8 minus 2 minus 1. That is 8 minus 3, which is 5. So what we're saying is this. For this graph, at an x value of 1, my y value is negative 1. But for an x value of 2, my y value is 5. Definitely not to scale. Because this is a polynomial function, it must be somewhere in here we cross the x-axis. We don't know where that is. This doesn't tell us where it is. It just tells us that there is one there. And that's it for this lecture. Thanks for listening.